Hi folks! The following video is going to talk about addition reactions to alkynes as well as keto-enol tautomerizations. Because alkynes have pi bonds similar to alkenes, they can undergo variations of a lot of the reactions we saw for alkenes. One reaction that alkynes can undergo, that we also saw for alkenes, is hydrohalogenation. For alkenes, this involved the Markovnikov addition of H and X across the alkene to generate a new carbon-hydrogen bond at the less substituted position and a new bond to a halogen at the more substituted position of the alkene. For alkynes, which contain two pi bonds, these can be treated with excess HX, where X is chlorine, bromine, or iodine, and this forms what's known as a geminal dihalide product. So Markovnikov regioselectivity is observed. There have been two new hydrogens added to the less substituted carbon, and two halogens added to the more substituted carbon. I won't talk about the mechanism in depth, but it does occur by addition first of one equivalent of HX to break one pi bond, install one new hydrogen on the less substituted position, and one new halogen on the more substituted position. Notice there is still an alkene present in this intermediate. And then, now that this is an alkene, we previously saw that alkenes react with HX, and Markovnikov addition again would get us to the final geminal dihalide product. A variation on hydrohalogenation that we saw previously in the case of alkenes was sometimes known as radical hydrohalogenation. This is the addition of HBr specifically in the presence of ROOR, a peroxide. These reagents, for which we haven't learned the mechanism yet, lead to anti-Markovnikov addition, where the more substituted carbon of the alkene has a new hydrogen attached, and the less substituted carbon has the halide added to it. This reaction is specific to HBr and not other halogens. In the case of alkynes, treatment of the alkyne with HBr in the presence of the peroxide ROOR leads to a product where anti-Markovnikov addition of HBr has taken place. I've added one hydrogen to the more substituted carbon and one bromine to the less substituted carbon. This occurred across one pi bond, leaving one pi bond remaining for an alkene product. This product could have two stereochemistries, with the new geometry being either trans or cis. We also previously saw addition reactions involving halogens, either chlorine or bromine. In the case of alkenes, halogenation leads to anti-addition of two X groups across the alkene. In the case of an alkyne, treatment with the same conditions but with excess halogen leads to formation of what's known as a tetrahalide, where four new halogens have added to the molecule. These two carbons of the alkyne are these two carbons that got the halogens added to it. Notice each carbon of the alkyne had two new halogens added to it. In this reaction, you would first react the alkyne with one equivalent of Cl2 or Br2. You would have anti-addition of the halide across the alkyne to generate an alkene intermediate, which has two X substituents, and then this alkene could react with another equivalent of the halogen to give ultimately the tetrahalide product. A final reaction that we saw for alkenes that will also be important for alkynes is ozonolysis. For alkenes, this was treatment with ozone followed by DMS, or zinc and water. The outcome of this reaction is that the carbon-carbon bond of the alkene is completely cleaved, and each of those carbons has a new double bond to an oxygen. For alkynes, the reagents are different slightly. You treat the alkyne first with ozone as before, but the second step is treatment with just water. In the case of a terminal alkyne, you imagine complete cleavage of the carbon-carbon triple bond, and each carbon of the alkyne has oxygens added to it. The carbon of the alkyne with other carbon groups attached gets turned into a carboxylic acid, and for terminal alkynes specifically, where you have a CH bond off of your alkyne, that carbon group gets turned into an equivalent of CO2. In the case of internal alkynes, ozonolysis leads to complete cleavage of the carbon-carbon triple bond again, but for internal alkynes, each carbon of the alkyne gets turned into a different carboxylic acid. So the formation of CO2 as one of the products is specific to terminal alkynes. The remainder of today's video is going to be dedicated to different types of hydrations of alkynes. The first one of these is called Mercury-catalyzed hydration, and it occurs in the presence of acid. For alkenes, recall that we saw that acid-catalyzed hydration can occur by treating an alkene with H2SO4 and water, or you could just write this as H3O+. These conditions lead to Markovnikov addition of a hydrogen and an OH group to generate an alcohol product. For alkynes, in addition to having sulfuric acid and water around, it's also important to have a mercury sulfate catalyst present. The initial product formed has a hydrogen added to the less substituted position and an OH group added to the more substituted position of the alkyne, with an alkene still present. This intermediate is known as an enol. The ene part of this name refers to the fact that it contains an alkene, and the ol part of this name refers to the fact that it has an alcohol coming off of the alkene. It turns out that these enols are short-lived, and they can undergo a reaction known as tautomerization to form a ketone instead. I'll talk more about this transformation a bit later in the video. So these three reagents, H2SO4, mercury sulfate, and water, cause both the formation of the enol and the subsequent formation of the ketone. The net effect of this was that hydrogens were added to the less substituted carbon, and a new carbon-oxygen double bond is present at the more substituted carbon of what was originally the alkyne. Before delving into the mechanism, I want to say a few words about the reagents. As we saw previously, recall that sulfuric acid reacts with water in an acid-base reaction to form HSO4- and H3O+. Based on the pKa's of the acid and the conjugate acid, the product side is heavily favored. So in our mechanism, we're going to use H3O+ as the acid catalyst. In terms of the mercury reagent, so mercury sulfate is a salt, and it can dissociate to form mercury in the 2+ oxidation state, and sulfate with SO4 2-. In the mechanism, we're going to use this mercury 2+ molecule as an electrophile. This mechanism is a bit of a long one, and I'm going to break it down into two parts. I'll call part A the enol formation mechanism, just getting us from the alkyne to the enol intermediate. The first step of the mechanism is reaction of the alkyne with the mercury. This is going to be a bit of an unusual nucleophilic attack. It's sort of a double nucleophilic attack, and it forms a 3-membered ring. I'll have 2 curved arrows, 1 curved arrow from the pi bond to mercury, and another curved arrow from the mercury lone pair to one of the carbons of the alkyne. This step forms a three-membered ring. I used one pi bond to form a new bond to mercury, but there is still a sigma and a pi bond remaining, so I still draw a carbon-carbon double bond. There's a three-membered ring of the two carbons of the alkyne with the mercury. This step makes the two carbons of the ring more electrophilic, and in particular this more substituted carbon is the most electrophilic site. If I bring in a nucleophile to this more substituted carbon, I'll put partial positive charge on a more substituted position at the transition state. I'm going to have a nucleophilic attack and loss of leaving group, and I'm going to use the water as the nucleophile. I'll bring in the nucleophile to the more substituted carbon, break that carbon's bond to mercury in the same step. This is opening up that three-membered ring. After this step, I have a new carbon-oxygen bond. Oxygen is cationic because it has three bonds, and the mercury has lost its bond to the more substituted carbon and is now only attached to the less substituted carbon of what was originally the alkyne. The carbon-carbon double bond remains in the molecule. In the next step of the mechanism, I'm going to deprotonate the cationic oxygen. Under these acidic conditions, the best base that I have present is water. I'll use a water lone pair as the base in this proton transfer step. This proton transfer gets to a neutral oxygen, the mercury remains attached to the other carbon, and the double bond remains. The next step of the mechanism is going to be a proton transfer. I'm going to use the pi bond of the alkene as the base here, and H3O+ will serve as the acid. I'll take the pi bond as the base to the proton and break the oxygen-hydrogen bond. I would add the new proton to the carbon with the mercury attached to it, so that I form a carbocation adjacent to the oxygen with lone pairs. This is one of our resonance patterns, empty p orbital next to lone pair, and I can draw a second resonance form by taking an oxygen lone pair and bringing it down to form a pi bond. In the other resonance structure, there is a carbon-oxygen double bond, and the oxygen is now positively charged. The last step of the mechanism, getting to the enol intermediate, is going to involve the loss of mercury. This is going to have two curved arrows. I will take the electrons from the carbon-mercury bond and use them to form a carbon-carbon pi bond, and I will break the carbon-oxygen pi bond and bring those electrons to oxygen. This step formed the pi bond of the alkene with the OH group attached to it, and mercury has been lost without the electrons from the bond that it formerly had to carbon, and it is back to a 2+ charge. I've regenerated the mercury here, which is good because it's serving as a catalyst for this reaction. Now I want to turn our attention to the second stage of the mechanism, the so-called tautomerization from the enol intermediate to that final ketone product. This is sometimes known as a keto-enol tautomerization. Under the mercury-catalyzed hydration conditions, H3O+ is going to serve as a catalyst for this reaction. The first step of the mechanism involves a proton transfer. Here, H3O+, the acid, is acting as the acid, and the pi bond of the alkene is acting as the base. I would take the electrons from the pi bond and bring them to the proton, break that bond to oxygen in that first step. I would add the proton to the less substituted carbon to make the carbocation adjacent to the OH group. There's resonance involving that oxygen lone pair. I could bring that down to form a pi bond. In the other resonance form of this carbocation intermediate, I have a carbon-oxygen pi bond, and oxygen has the positive charge. And like we've seen previously, resonance-stabilized carbocations are extra stable compared to typical carbocations. To get to the ketone final product, I need to deprotonate the cationic oxygen. Under acidic conditions, where I have H3O+ and water around, water is the best base that's available. I'll use an oxygen lone pair to deprotonate the cationic oxygen's hydrogen in this proton transfer step. This would form the ketone product of the tautomerization step, and the proton transfer involving water formed H3O+, the conjugate acid. It's good that I've reformed this in the final step of the mechanism because I said earlier that it serves as a catalyst for this reaction. I want to talk a bit more about this keto-enol tautomerization. The term tautomers refers to molecules that are constitutional isomers, but that are rapidly interconverting, going back and forth between one form of the molecule and another at equilibrium. As I mentioned earlier, the term enol specifically refers to a molecule that has an OH group coming off of an alkene, and enols exist in equilibrium with ketones. The conversion between the enol and the ketone, going back and forth, is known as the keto-enol tautomerization. Typically, the ketone form of the molecule is favored over the enol form, and the conversion between the enol and the ketone is catalyzed by either acid or base. This will typically be drawn as H3O+ or OH-. For now, I want to talk about the acid-catalyzed variants of this tautomerization reaction. And first I'm going to consider the curved arrow mechanism going from the enol form to the ketone. And after this we'll do the reverse. The first step of the mechanism is a proton transfer. The alkene of this molecule will act as the base in this step, and H3O+ will be the acid, because I specified that we're looking at the acid-catalyzed conditions. I would take one curved arrow from the pi bond to the proton, break that hydrogen-oxygen bond, and bring the electrons to oxygen. I would add the proton to the carbon of the alkene without the OH group present, so that I form the carbocation adjacent to the oxygen. I do this because I want that carbocation to be resonance stabilized and therefore more stable. To draw the other resonance form, I would take a lone pair from the oxygen down to form a pi bond. In the other resonance form, there is a carbon-oxygen double bond, and oxygen has 3 bonds and therefore has a positive charge. To get to the ketone form, I need to do a proton transfer to deprotonate that cationic oxygen. Under acidic conditions, the best base I have available is water. So I would draw the 2 curved arrows for the proton transfer using water as a base. This step would form the ketone as well as regenerating H3O+, the acid catalyst. So looking back at this mechanism, notice it involved 2 steps, both of which were proton transfers, and in the middle of the mechanism I had a resonance-stabilized carbocation. Now let's consider the reverse reaction, because I mentioned that the ketone and the enol are in equilibrium, so you may be asked to draw a mechanism going from the ketone to the enol. I'll begin the mechanism with a proton transfer. I'm going to use the oxygen of the ketone as a base, and H3O+ as the acid. I'll draw this using an oxygen lone pair in the 2 curved arrow step. After this proton transfer, the oxygen has a hydrogen attached to it, and it is now cationic. This molecule contains a polar pi bond, so there is another resonance form that can be drawn. I would break that polar pi bond and bring the electrons to the more electronegative atom, in this case oxygen. In the other resonance form, I would have a neutral oxygen and a carbocation. To get to the final product, I need another proton transfer. Here I'm going to use water as a base, and I'm going to deprotonate a position alpha to the carbocation. So I drew out a carbon-hydrogen bond at this position. I'll use an oxygen lone pair to form a new bond to the proton, take the electrons from the carbon-hydrogen bond, and use those to form a carbon-carbon pi bond. This proton transfer step would create the enol form of the molecule and regenerate H3O+, the acid catalyst. So looking at this mechanism as well, notice that it was a two-step mechanism, both of which were proton transfer steps. And notice that the intermediate in the middle was a resonance-stabilized carbocation. This is the same carbocation intermediate that I had in the previous reaction, the reverse reaction. Another variation on hydration that we saw previously for alkenes was hydroboration-oxidation. For alkenes, this involved treatment with BH3-THF, followed by treatment with H2O2-NaOH, and the net effect was anti-Markovnikov hydration. The reagents for the reaction involving alkynes are similar. One change is that I'm using R2BH instead of BH3. I'll give you some structures for these boranes a bit later on the slide. And the alkyne hydroboration-oxidation initially forms an enol intermediate. In this intermediate, I've broken one of the pi bonds, but one still remains. I've added a hydrogen to the more substituted carbon and an OH group to the less substituted carbon. So I've had anti-Markovnikov regioselectivity again. But here as well, this enol intermediate is unstable, and it will tautomerize to form an aldehyde product. I'll show you this mechanism for tautomerization, and it's going to look a little bit different because here I have basic conditions, NaOH instead of H3O+. So, why do we use R2BH instead of BH3 here? A challenge with alkynes is that they contain two pi bonds instead of just one, and BH3 is small and very reactive, and it can add to alkynes twice. So let's consider you wanted to add a BH3 molecule to an alkyne. BH3 would react in an anti-Markovnikov manner. You would have a syn addition of the hydrogen and the BH2 group to the alkyne, with the BH2 added to the less substituted carbon. You would still have one pi bond remaining. The problem would be that this alkene that you formed could also react with BH3 to give another addition of a hydrogen and a BH2 across this molecule to give you a molecule with two BH2s present. And this is undesirable if you're trying to get to an aldehyde product. What you can do is use a bulkier borane than BH3, which I'm going to shorthand as R2BH. Two variants that you'll see in the textbook are diisoamyl borane, this really bulky one on the left, and more commonly you'll see one called 9BBN. So if you see either of these names or just R2BH written out, these are conditions for hydroboration of alkynes. In this reaction, the first step is treatment of the alkyne with R2BH, and there would be a very similar reaction to what we saw for alkenes in this case. You would break one of the pi bonds of the alkyne, add the hydrogen to the more substituted carbon and the Br2 group to the less substituted carbon. This is known as a vinyl borane intermediate. Treatment of the vinyl borane with H2O2 and NaOH would convert this molecule to an enol by the same mechanism we saw in the case of alkenes. When you form this enol, it's in the presence of NaOH, one of your reagents of the second step, and this hydroxide is actually going to serve as the catalyst for the tautomerization of the enol to the aldehyde product. I'm going to start with the enol, and this is in the presence of hydroxide, which is going to serve as a base and a catalyst for this reaction. The first step is a proton transfer, and it's the OH of the enol that can be deprotonated. I would have my two curved arrows of this proton transfer step. After this proton transfer, I've formed the conjugate base, where I have an anionic oxygen attached to an alkene. This is one of our resonance patterns of lone pair adjacent to pi bond. I can draw another resonance structure by taking a lone pair down to form a pi bond and taking the pi bond over to form a lone pair. In the other resonance form, there is a carbon-oxygen pi bond, and the adjacent carbon has a new lone pair and a negative charge. So this anionic intermediate is resonance stabilized, and it's known as an enolate anion, the conjugate base of an enol. This anionic carbon in this resonance form of the enolate can act as a base, and it can be protonated to form the aldehyde product. To protonate this, I need an acid, and because I'm under basic conditions, water is the best acid that's available. I would use the carbon lone pair as the base, and water as the acid in this proton transfer step. This step generates the aldehyde product, and it regenerates hydroxide, the catalyst. So, this is our base-catalyzed tautomerization mechanism. It appears in the hydroboration-oxidation reaction, and similar to the acid-catalyzed tautomerization, it involves two steps, both of which are proton transfers, and the intermediate is resonance stabilized. Alright, so now I've shown you two variations of alkyne hydration. So let's imagine we're starting with this alkyne in the middle and trying to figure out reagents to either generate this aldehyde or the following ketone. These two carbons of the alkyne are these end two carbons that are either present in the aldehyde and its neighbor or the CH3 group and the ketone. These two products differ in whether I had Markovnikov or anti-Markovnikov addition to the alkyne. To generate the aldehyde product, an anti-Markovnikov hydration had to occur, and I had to have a less substituted enol intermediate. This would then tautomerize to the aldehyde final product. To get this regioselectivity and form the anti-Markovnikov product, the aldehyde, you would want to use hydroboration-oxidation conditions. To get to the ketone product, you would want Markovnikov hydration to occur, where you've added a hydrogen to the less substituted carbon and the OH group to the more substituted carbon. And when it tautomerizes, this would get converted into that ketone where the CO double bond is second from the right. For alkynes, Markovnikov hydration occurs when you treat the alkyne with mercury sulfate, sulfuric acid, and water. Okay, so in this video I introduced many types of alkyne addition reactions. These are similar in most cases to what we saw previously for alkenes. And I talked in depth about mercury-catalyzed hydration and hydroboration-oxidation. Both of these reactions form an enol intermediate, so I also talked about keto-enol tautomerizations, and how these tautomerizations can convert an enol into either a ketone or an aldehyde. That's it for this video. I will see you in class.